Okay. I've tried to make this video a couple times. It hasn't worked. I hope it works this time. We're going to look through chapter 3 really quick and try to learn as much as we can. We'll try to get through 3 sections, I think. So in chapter 3 we're talking about kinematics in 2 dimensions, which actually we've already done when we switched from x-dimensional kinematics to y-dimensional kinematics in the last chapter, going up and down instead of side to side. That's kind of the first step in going to 2-dimensional kinematics. But we're going to talk a little bit about vectors here in 2 dimensions. So let's start off with a very simple system in a rectangular coordinate system. We have somebody walking through a city here from left to right in the positive x direction, or east in this case, and then they walk 9 blocks east, and then they walk 5 blocks north, and these can be represented as these vectors, and you can represent the displacement of this person as an overall vector from their starting point to their ending point, and you can calculate that using the Pythagorean theorem. So if you want to calculate that final distance, you take the 2 short legs, the east leg and the west leg, and you square them, add them together, and take the square root to get that long leg on the hypotenuse side of the triangle right here. And if you do that, you're going to get 10.3. It ends up being longer than either of the short legs, which we would expect. And so that's one of the tools that we use in 2-dimensional mechanics, 2-dimensional kinematics rather. We have 2 dimensions, x dimension, y dimension, and we can calculate a vector that is in both dimensions. It has not just an upward movement, but an upward and sideways movement. So that is in 2 dimensions now from those 2 other vectors that were each in one individual dimension. Now, it's important to note that and to recognize that motion in perpendicular directions is independent of the other dimensions. So one of the experiments that can be done to show this is the dropping ball and the thrown ball at the same time. So you have this red ball here that you drop straight down, and these arrows represent the velocity vector. Over time it gets faster and faster and faster as it accelerates down towards the ground due to gravity. Excuse me. But then you have another ball that you throw horizontally at the same time. And once you let go of the ball, there is no force pushing the ball to the right. It's just going as fast as you threw it, and it maintains that same velocity to the right. However, it still falls to the ground just like the falling ball, just like the ball that you drop straight to the ground. So it drops a little bit faster, more and more as it accelerates due to gravity again. And so the thrown ball and the dropped ball will hit the ball at the same time if they are thrown and dropped at the same time, and as long as this ball is thrown perfectly horizontally or perfectly perpendicular to its vertical movement. And that independence of motion is extremely important. It makes the physics doable, really. And why does it make this physics so that we can actually do it? It has to do with math of vectors, in fact. So let's talk a little bit more about vectors. In 2 dimensions, where we have maybe a north and a south, an east and a west, or we have a positive y and a negative y and a negative y and a positive x, you can have somebody take several vector paths. So this solid line here would represent a trip that somebody maybe takes by airplane from city to city to city to city to city. And if we wanted to calculate their overall displacement, we could do that. We could put all these vectors on here and go from the beginning of the first vector to the end of the last vector. And this is what we call vector addition, graphical vector addition, or another way that they call it is the head-to-tail method. And in that case, what we can do is if we go back to our example with the street, walking along the streets, we can take our 9 blocks east vector and our 5 blocks north vector, and we can add them up to make the resultant vector that, say, a helicopter might fly between those 2 points. And we do this by taking the first, we go here, We take our first vector, our 9-unit vector to the east, which is the 9 units to the positive x, and then we put the 5 units north, or the 5 blocks north vector on the head of the first vector. So we're going head to tail here. And then we go from tail to head to create the new vector, and we draw a new vector from the tail of the first one to the head of the second one, put an arrow on it, and we can go ahead and measure that and get 10.3 units. We can measure the angle here, get about 29 degrees. And this is called the head to tail method, or the graphical adding method for vectors. It is not extremely precise because you have to be very good and very careful drawing these things in order to get these numbers just right. If you're off a little bit on the angle or a little bit on the distances, then your whole measurement will be off. But it's pretty good for basic ideas, to get a basic idea of where vectors are going to. And you can do this with more complex vectors as well. Let's say we have these 3 vectors, 25 meters kind of northeast here. We call this 49 degrees north of east. And we measure angles from the x-axis counterclockwise and to be positive. And then this one is 15 degrees north of east, 23 meters long. This one is 68 degrees south of east, and usually this would be called a negative 68 degrees, but either way it works out. And this one is 32 meters, of course. And then if we add these 3 vectors together, we can do that graphically by putting them head to tail to head to tail. Notice that we just move these vectors around. Put this b vector on the a vector, put the c vector on the end of the b vector, then a plus b plus c equals the vector that you draw from the beginning of a to the end of c. And if you draw that, it's about 50 meters long at about a 7-degree angle down from the x-axis. But you notice also that if you mix up the addition, if you do CAB, for example, or if you do BAC or BCA, it will always end up in the same place where you have a 50-meter vector and a 7-degree down 7-degree down angle from the x-axis. So vector addition is commutative. You can move it around, which is nice. Now, vector subtraction, of course, subtraction is just another form of addition. It's addition of negative numbers. And that's a really good way to think of it with vectors. If you have a vector b that is upward and to the right like this, the vector negative b will just be the same line with the arrow on the other end, pointing the other direction. And so negative b is just the same vector, same length, same angle, just opposite direction. And if you want to do the vector subtraction a minus b, then it's the same as doing a plus minus b. So if I take the a vector and add the negative b vector, which would be this one, I will get the proper vector graphically speaking. So here are the a and b vectors. If I want to do a minus b, then I go ahead and create the minus b vector, which is minus b like this. And then I add them graphically, a plus a minus b, and this gives me my resultant vector, turns out to be this one here. Whereas a plus b would look like this, the resultant vector. That's why they use r for the answer. R is equivalent to resultant. Now, multiplications of vectors and scalars. Multiplication of vectors, we're not going to multiply vectors together in this class. The math is beyond the prerequisites for this class. If any of you are going to take the calculus version of this class later, or the calculus addition to this class later, then you will learn some of that. But that's beyond the scope of this class. However, we can multiply a vector or divide a vector by a scalar. What is a scalar? A scalar is just a number like 3, 4, 2.5, whatever. But it doesn't have direction, it just scales the vector. And a scalar can be positive or negative, it can even be 0. And it can make the vector longer, or it can make it shorter, or it can flip it around. It can make it go the opposite direction. If your scalar is negative, it can turn the vector the other way and also make it longer or shorter depending on the number. So scalar multiplication is perfectly fine with vectors, and it just makes the vector, like I said, longer, shorter, or negative and longer and shorter. Same with division. You can also divide by any scalar, which is, of course, division is just a version of multiplication. But we don't want to necessarily do everything graphically because it's difficult to do the math of physics graphically. You want more precision than that. And so what we do is we're going to break down our vectors into components. components that are perpendicular to each other because the coordinate systems that we are going to use are perpendicular to each other. X and Y are 90 degrees from each other, so they are perpendicular coordinates. And if you look at this vector A, you will notice that it does have a certain amount of upward pointiness. It's pointing upward a little bit, right? And essentially what we can do is if we go along the y-axis up from the base of the vector A all the way to the top of the vector A along the y-axis, and we make a little vector there, and over here they've put it on this side, and that's fine. We go from y equals 0 all the way up to the top of the vector. This is what we call the component, the y component of A, or A sub y. And this vector tells us essentially how much distance the A vector goes in the y direction. And there's another one for the x direction. If you go where x equal, here we're going where the beginning of from the beginning of the A vector, or where the A vector starts out here. So if the A vector is out in the middle of the field here somewhere, you can do this as well. But the A vector starts at the origin in this case, not always the case. But it starts at the origin, we go over here, and we keep going along the x-axis until we hit the end of the A vector here perpendicularly. And that would be our A component, x component of the A vector. Some people like to think of it as shining a light down on the vector towards the x and y axes, and the shadow that the A vector would cast on those axes would be the length of the component, and the direction, of course, would match up with the direction of A vector. Sometimes you'll hear the components of a vector referred to as the projections of the vector, as if you're projecting a shadow onto the axes in that way. So sometimes that's the case. But these components, as you can see, if you add them up graphically like we did in the last section, head to tail like this, they actually add up to equal A. So A sub x plus A sub y equals A, or the components of A add to equal A, always. Right? Now, of course, if this vector was pointing down this direction, it might have negative components, negative x and y, or one negative y component and a positive x component, or whatever else. It depends on which way it's pointing, determines what signs these components might have. In this case, they're both positive components because this one is pointing off into the positive x direction and this one's pointing off into the positive y direction. But they can point anywhere depending on which way the vector is pointing. But you'll notice that with this particular vector, if the side of this vector is 3 and this one is 5, sorry, this one is 4 rather, let's see, that's not true. They're doing a bad example here. So anyway, for all right triangles, you can't just add triangles. You can't just add these two. You have to use the Pythagorean theorem. If you know the length of A sub x and the length of A sub y, or you'll get the wrong answer for A if you just do it. The Pythagorean theorem. Go ahead and calculate the length of A, and that's what they're talking about down here. I thought up here they were doing the theory wrong, so I was checking that, but they're not. But the more important thing, I think, to realize, if we know the components of these vectors to a very high precision, and you do that using trigonometry. So of course, if this is a right triangle, which it is, we have this right angle here because the x components and the y components are always perpendicular to each other. And we know the angle theta here. This is an angle that we know about or we're interested in, either way. We can actually use the length of the A vector and the trigonometric identities to calculate this side of the triangle and this side of the triangle. And this comes from you've probably heard of before. If you haven't, we'll refresh, or we'll teach it to you really quick. So with SOHCAHTOA, the hypotenuse, you can relate, well, even if you don't know them, but the relationships are always the sine of the known angle. So if you take the sine of this angle, it is always equal to the opposite of our hypotenuse. That's the sine opposite hypotenuse. If you take the cosine of the angle that you know, it is always going to be equal to the adjacent side, which is the side nearest the angle, divided by the hypotenuse along the side. And then if you take the tangent of this angle, it's always going to be equal to the opposite side of the adjacent side. So that's the Ch3a part. And that helps you to remember that, in case you don't remember, in case you haven't learned that before or whatever. And so in this case, if we have this triangle and we want to calculate the x component, it is the x side here, this x component, is next to the angle theta, so we use the cosine, and we solve that relationship, and we get that, we find that this adjacent side equals the hypotenuse side, which is the length of A here, times the cosine of theta. So that's just the solution of the Ch3a thing. And then on the y side, you get A sub y equals A sine theta. Now, if you know theta, if theta is this angle here between the x-axis and your vector, then these work. However, if you know this angle up here and you're trying to calculate this one to this one, it's a little bit different. For the x one, you'll use the sine. For the y one, you'll use the cosine. We will see situations where you do that. But if you remember your trigonometric identities, it doesn't really matter. You can set it up any way you want and figure it out. So here's the example of the street again, where we go 9 blocks and then 5 blocks. Let's see if this works. Let's work this backwards and see if we can calculate 9 and 4 from the 10.3 that we measured when we did it before. So 10.3 is the length of the vector A, or the displacement vector across the hypotenuse here. We plug that in, 10.3, cosine of 29.1, which is the angle we measured, and we get about 9 blocks. And the same thing for the other side, the sine side, which would be this one over here, which, you know, you could slide over here and make your triangle. But then you get 10.3 times the sine of 29.1, you get 5 blocks, and it works out pretty well. And if you want to calculate that, check out that 10.3 to see if it works, you could add this 9 and 5, you know, squared together and get this, but that's how we did it anyway to begin with. So anyway. Now here's the real doozy. Here's the real power of this idea. Let's say that we have two vectors, A and B, this red vector and this blue vector, and we want to add them together to make the vector R, where we did it before by doing the head to tail method and drawing this in and measuring and everything else. But what if we want to do it and know much more precisely what the answer really is? Well, what we do is we break down, or we resolve. We say that we resolve these vectors into their components. The A components are going to look like these red A components down here, A sub x and A sub y. So you calculate those. Then the B one, notice that the B one starts out here and only goes a little way because the B vector only moves a little bit in the x direction. And then it starts up here and goes quite a ways up in this direction. But the resultant vector, notice here, meets where the sum of these components meet. In other words, the resultant vector R sub x is equal, the component, the x component of the resultant vector R sub x is equal to the x component of A plus the x component of B. And the y component of the resultant vector Ry is equal to A sub y plus A sub B. Sorry, A sub y plus B sub y. Sorry, there we go. So essentially all you need to do is figure out what these components are of each individual vector, and then add all the x components together, add all the y components together, and create a new vector. Once you've found these new vector components, Rx and Ry, you can use them to find the length of R using the Pythagorean theorem right here. And you can even find the angle between the x-axis and the R vector by using the tangent. Remember that the tangent was equal to, the tangent of the angle was equal to the opposite side over the adjacent side, which would be Ry over Rx. And your calculator can do that calculation backwards. If you plug in the length of Ry, or the y component, divided by the x component, and then take the inverse tangent, which is usually tan negative 1, but sometimes it's also called the A tan, so A-T-A-N, then it will calculate that angle for you, and then you know the angle. And they do it for us. They do this exact problem for us. We start off with two vectors, A, which is 53 meters, and B, which is 34 meters. They give us the angles, and then down here they calculate the x component of A. A, which is the 53 meters, times cosine 20, gives them 49.8. And then they calculate the x component of B. B times cosine theta B, 34 times cosine 63, They get that one. So here are the two x components, the x component of A, the x component of B. That is right here, the x component of A and the x component of B. Add them together to get the total x component of R, right? They do the same thing in y. Calculate the y component of A using the sign this time, and the y component of B using the sign this time. And then you have Rx and Ry by adding them together. Ax plus AB, Ay plus By. And that will tell you the length of the R components in x and y. You take those two lengths, you square them, you add them together, and you get the total length, after you take the square root, and you get total length of the R vector. And then you take the y component divided by the x component, take the inverse tangent with your calculator, get 36.6, and you know what that angle is now. And now you know where this R vector is supposed to be. It works for subtraction as well. If you want to do A minus B, then you do A plus minus B. You create the minus B vector, which would go downward to the left, and then you just add it to A. So A plus a minus B. You can do the whole head to tail thing, but really what you're going to end up doing is you're going to take components. You have the A component is pointing upward. The B component, because it's minus B, is going to point downward now. And you get A plus a minus B. And when you add those together, of course, you're going to get an overall negative y component for R. For the x components, you have A, which is pointing off to the right, this big red line here, and B, which is just a tiny little thing back to the left. So A plus negative B ends up being positive still in the x direction, and it's pointing downward to the right for the resultant vector. So that takes us through most of the chapter. That takes us through 3 sections of 5 out of this chapter. I'm going to leave projectile motion for Monday, or for Tuesday rather, so that we can talk about it in class. It's a little more involved. We'll get some practice in for projectile motion in class, but this should get you started for your chapter 3 homework. And I've extended that on to out to a later date so that we can finish up chapter 3, and hopefully we can get on to 4 and 5 next week and the week after, and we'll be good to go. Have a good one.